See, okay? Okay, so okay, capacitors. Remember, they're called capacitors because they have the capacity to store charge. So, to store charge and energy. What is a capacitor? A capacitor is essentially you have two. I'm going to draw 3D plates because I'm amazing at art. Okay, you have two plates, and they're separated by an insulator. Okay, um, you guys did that first piece that essentially you guys should have gotten that from that first lab because the idea isn't it hopefully it makes sense that the bigger the area of these plates the more charge it can store. Okay, um, the closer the two plates are together, if I connect this to a battery, okay, the closer the plates are to each other, the easier it is to scare charge off the other side. So, like, if the plates are super far apart, it's harder to scare charge off the other side. So, not as much charge builds up. Do you guys follow that okay? And then this is just a constant. And this is, it's called the dielectric constant. But it would be like if you're putting some in a different insulator inside. And when you put a different insulator inside, that would allow you to build up even more charge. Okay, which that everybody follow that? Okay.
Can you explain the dielectric, like how it like specifically works? I guess.
Sure. All right. So if I have the two plates, and I have okay, this is my insulator, which is the dielectric. Okay. If this thing is building up a positive charge, so let's say right now I have how many? 5 charges on each side. Okay. Well, this dielectric, what's going to happen, because it's an insulator, you're going to get this positive, negative, positive, negative. It's going to kind of look like this. That's polarization. You with me there, Anshul?
Yeah.
So just from having this thing here, from having this buildup of charge here, do you see how now I can build up more charge on each of the plates? Because now for example, I can get more negatives to attract the positives in this insulator. I can get more positives to attract these negatives over here. So rather than having 5 charges on each plate, now maybe I can get 9 charges on each plate or 10 charges on each plate. Does that does that make sense?
Yeah.
If I went from 5 charges on each plate to 10 charges on each plate, then my K would be 2 because I doubled the capacity. I doubled the capacitance. All right, that piece okay?
I have a question.
Go.
So, what exactly happens when the capacitor gets discharged? Then,
So when a capacitor gets discharged, so let's say you have a light bulb here, okay, and you're connecting your capacitor to this. So literally, what is happening is this charge is working its way back around this way. And over time, like, hey, I lost a charge here and I made this side neutral. I lost the charge here, I made this side neutral. And then eventually your your capacitor doesn't have any charge anymore.
okay, thank you.
Yep. Which is why this graph is super duper important. This QV graph is super important. So that as you're building up charge, like, hey, if you have your capacitor and it's uncharged at the start, well, it has no charge, it has no voltage across it. As you build up charge, it goes this way until you get to a point where like depending on your circuit, like this upper limit, it all depends on your circuit, and it depends on how much voltage can build up across there. It depends on if you have a series circuit, a parallel circuit, whatever. Okay, if it's just hooked up to a battery, this will end up being the voltage of the battery. Everybody still okay? And then if you have something that has a bigger capacity to store charge, well, hopefully it makes sense. Like, its graph would look like this. At a given voltage, it can store more charge. Okay? Which is why the slope of this graph is your capacitance. And then just remember, the area is your energy that's stored in it. That's why if you look on your formula sheet, you'll see this there. If you look on your formula sheet, they write it. I always think of it because I always think of this graph. So whenever I write it, I think like C equals Q over V. But the College Board, when they write their equations, and if you look on your equation sheet, they write it like this: Q equals C times V. The reason the College Board does that is they like to always have the variable over here depends on these variables. Do you guys with me there? Okay. So I always do it like I always write it like this because I always think about this graph and I think about the slope. Okay. But the College Board, if you look on your formula sheet, it's written like this because capacitance doesn't really depend on Q and V. It depends on this stuff. It depends on like the physical makeup of your capacitor. That the amount of charge that builds up depends on your capacitor and it depends on the voltage. Do you guys understand that okay? If you look on your equation sheet, it's also written like this. But I'll be honest, I don't understand. The College Board doesn't always make sense to me because it's like, hey, I don't want you guys to have to do algebra. I'll just tell you this one, but then other times they don't tell you the algebra. I don't know. But anyway, both those equations are on your equation sheet. Okay. All right. Basics on what a capacitor is, how it builds up charge, how it discharges. Are you guys good with that? Anshul, I'm not convinced.
No, I'm good.
Okay. All right. So then we did there, a lot of it where you had the circuits like this. If I have a capacitor here and some light bulbs like this, where you have to be able to do the initial state, the final state, the steady state, and be able to explain things. Or if I have a capacitor like, if I have a circuit like this and a capacitor here, can you do the initial state, the final state? If I have a circuit like this, that type of thing. Are you guys good with these type of problems?
Yeah, I have a quick question. If there was like a battery in a circuit, if there was a battery, then a resistor, then a battery, then a resistor, can you just add the batteries together, even though there's resistors in between?
Only if they're situated the same way.
So okay, yeah. If it's like, but then you would subtract it if it's opposite directions.
Yeah, right. Yeah, if it was like that, then you could just add them together. Where if it was like that, you would have to subtract them.
Okay. Thanks.
Like one thing for these circuits.
Mm-hmm.
So like I remember for one of the labs, it was like it follows basically like the path with like no resistor on it. So then in this case, or like in the top one, it would go through both though, right? Because they both have resistors for the parallel path.
Are you talking about this one?
Yeah.
All right. So yeah, here for this circuit, guys, what would happen at the very start and then after it reaches the steady state?
current would flow through the whole circuit.
Yeah, you would have, it would just be like, and then after it reaches the steady state, what would happen?
Current wouldn't flow at all.
Current wouldn't flow at all. All right, which one of these 3 circuits, okay, which one would, after it reaches the steady state, is the voltage of the capacitor going to equal the voltage of the battery? I'm going to make this, see, I can't really do multiple choice this year. I'm going to make that as one of my multiple choice questions for next year.
Is that like the bottommost one?
Anshul, you picked the only one that it's not the case.
Wouldn't it be the top left? And
actually, top left, yeah. Yeah, okay.
All right, so let's talk about it. Okay, so remember, guys, loop rule has to be true. You guys with me there? Okay, like that, it has to be true. So when this thing is fully charged, do you guys understand that it's going to shut down the current flowing in the whole circuit? Well, you still have a circuit though, because there's still a way. So that means the voltage here has to equal the voltage here, because it's going to be nothing and nothing. Does everybody with me there? Okay, like if you were writing the initial, if I give these some numbers, okay, if I was going to write my initial loop rule equation for this, let's say I'm going to go around that bottom loop like that, okay? My initial loop rule would be the voltage from the battery, and then minus I2 R2 minus the total current times R1 equals 0. Do you guys understand that? Well, if you're doing it at the end, when this thing is fully charged, there's no more current. So then it would just have to be the voltage of the battery minus the voltage of the capacitor equals 0. So therefore, the voltage of the capacitor has to equal the voltage of the battery. You guys with me there, okay? And that's going to be the same in this one as well. If you look, does everybody see how when this thing gets fully charged, no more current's going to flow through this resistor? Which then means, do you see how if I do a loop, that means the only things in that loop are my battery and my capacitor. Which means then the voltage of the battery had better equal the voltage of the capacitor. Where if I do this circuit and I was to take this loop, do you guys see when it's fully charged? Do you see how I still have a resistor in that circuit that's going to be working? Do you guys with me? So then that would be the case where the voltage here is not equal to the voltage of there. Is that okay? Anshul, like I sometimes I think this means I don't really get it. Is that
no, makes sense.
Am I reading your body language correctly?
No, it makes sense.
Okay.
I get it.
See, like I have some students that are a little bit less subtle. They just do like one of these, and then I'm like, oh, I got it, I got you, no problem. I understand where you're coming from. All right, but do you guys feel okay with those? Do you want me to talk more about them?
I'm good.
We're okay?
I'm also good.
Okay. Then honestly, the rest of this unit is just, can you solve capacitor circuit problems? Series, do you understand the series rules, the parallel rules, combo circuits? And I can go over that with you if you guys want, or I don't need to if you guys feel like you got it. What do you think?
Could you just quickly go over the rules for the series and parallel?
I sure can. All right, so here, let's just make sure. Okay, so as I add capacitors like this, okay, first of all, is everybody okay with why it's a series circuit? There's only one path? Okay. So there's only one path for the current, so it's a series circuit, or for the charge, so it's a series circuit. But if you go back to our equation from before, remember this equation? Okay. If we look at, I'll just color it in red. Those would be my positive plates touching the battery. Does everybody with me there okay? The green will be the negative plates touching the battery. So if you take a look, can everybody see how really what's happening is the D, the distance between the plates that are touching the battery, is going up. Does everybody see that? Which means, remember how we talked about it's going to be harder to scare the charge off? So if it's harder to scare the charge off, then that means it's going to be harder to store the charge, so it's going to have less capacity to store charge. The capacitance is going to go down. So if you look at your formula sheet, you guys got your formula sheet? If you look on there, you will see where it says this, 1 over CS equals the sum of 1 over CI. Do you guys see that on there? What that is telling you is that, hey, to find your total or your equivalent capacitance in series, you have to add up the inverses and then flip it, okay? But what this is really saying is that when you add capacitors, your total capacitance goes down. Everybody understand why? Okay. So that's the first piece. So and then the second piece is that for a given circuit, okay, this is really kind of talking about like comparing circuits, but for a given circuit. So like if I have this circuit, well, remember the way that charge builds up in your capacitor is like, hey, I put a charge on this positive plate, that scares the charge off the other plate. Well, where does that charge go? Over to this positive plate, and then it scares the charge off over here. Do you see why the charge has to be the same on all the different capacitors, even if they have different capacitance? So in a series circuit, that your charge, your Q total equals your Q1 equals your Q2, and so on. The charge has to be the same everywhere. Good?
Can you explain, like, I'm kind of confused because when you add capacitors in series, isn't there also more area? Or like,
but there's not more area that's touching the battery.
Oh, so it's whatever's touching the battery? That's the area?
Yeah.
Oh, because like in a parallel circuit, they're all touching the battery because they're okay.
Yep, you got it. And then just remember, loop rule has to work. So obviously, in a series, it's going to be this, and so on. Everybody follow? Okay. Anshul, good. Okay.
I have a question about so the total capacitance follows that formula, so the total capacitance of like the entire circuit, but then obviously the capacitance of each single one would be the same, right?
And so the capacitance of each single one is determined by that.
Right. And but then the total capacitance would be that like 1 over like the inverse formula.
Correct.
And then you would calculate but you can calculate the charge for. So yeah, actually, I think this might be a stupid question, but like, how would you calculate the charge if you're given like the individual capacitance of each single one?
Okay, so here let's just do a quick problem.
Okay.
Let's go with 40 microfarads, 40 microfarads, 20 microfarads. Okay, so here's where you just have to be careful. If these were hooked up individually to the battery, so like I just hooked up the 41 to the battery, I just hooked up the 41 to the battery, I just hooked up the 21 to the battery. Individually, these 40s would get twice as much charge as this. You with me there?
Right.
But collectively, because they're in a series circuit, and the way charge builds up, like whatever charge builds up on this has to also build up on this, has to also build up on this. So collectively, the charge on all of them are the same. So whatever charge is here has to be there, has to be there. Do you understand that? Okay, Sahan. Okay, so if we were to do this, you got a calculator? I picked 40 and 40 and 20 because I can do this in my head. Because do you guys know that these two, when I combine it, it's going to be 20? And then I'm going to have a 20 and another 20. So if I combine that, it's going to be 10. You guys with me? Or you can just do it on your calculator. And we'll say this is 10 volts. Sahan, so far so good?
Yeah, that makes sense.
Okay, so then if you take a look, are you okay that this times this is going to tell me I have 100 microcoulombs of charge stored in that capacitor?
Yeah.
Well, that means that each of these capacitors will have 100 microcoulombs of charge.
Okay.
So then you could find the voltage for each of them as well. It'd be 4 volts, 4 volts, 2 volts.
You would get that by just doing yeah, okay. All right. Yeah, that makes sense.
Now, Sahan, let's go. Let me just show you. Okay. If this was your circuit, so if you had 10 volts and this was 40 microfarads, okay, this circuit would actually have 400 microcoulombs in it.
Right.
Because the overall capacitance is 4 times higher than this circuit was. So it's going to store 4 times as much charge as this circuit at the same voltage. But because I added these other capacitors in series to it, I just made it so that the whole circuit can't store as much stuff.
Right. So it's just like you just kind of have to, if it's in series, you just kind of have to think of it as like one big combined capacitor, unless obviously you're trying to calculate for the individual voltages across each one.
Yeah, which is why I would, Sahan, draw it out. Like do this step. That if you go and you do this step and then you work backwards, I could almost guarantee you will always get it right.
Okay.
You know. Yeah. All right. Is that good? Anshul, Esther, good? Jaden, good?
Wait, really quick. Just like I know you didn't like calculate the math or anything, but like for the 40 microfarad capacitors, wouldn't they have to be less than the 20 microfarad capacitor for the voltage it has?
Why?
Because like, I mean, if it has like, I just like calculated it kind of, but like, it would just like come out as less, right?
It would be for. Oh, you're right. Yeah, I'm sorry. So let me do. Yeah, let's do it. It would be.
I think it'd be 2.5, 2.5, and 5.
2.5. Yeah. Okay. Yeah, because it would be 100 divided by 4, so or 40. Thanks, Anshul.
All right. Cool.
Yeah, you're right. Thank you. Are we good? Okay. So then, parallel. So again, if we think So, kind of doing the same thing we did before. Can you guys see, like, do you see how the area is going to be bigger that's touching the battery? You know, so because that area is bigger, when you add capacitors in parallel, the total capacitance goes up. Which if you look on your formula sheet, you'll see that on there. And then, you know, the voltage is going to be the same everywhere, which is really just loop rule. But then you could also do, you know, like, you could say junction rule, so that the total charge has to be the sum of the individual ones. And then, do you guys want me to do a sample parallel, or do you feel like we're okay?
You do a sample parallel.
I would love to. All right, so here. So we'll go with 40 again. 40 and 20. And we'll have a 10-volt battery, just like we did before. All right, so if I was going to simplify this circuit, the equivalent capacitance of this circuit would be 40, 40, 100. Everybody understand why? And then you could solve for the capacitance or the charge by multiplying these. So it would be 1,000 microcoulombs. Where before, if you remember, we had the same, it was 100 microcoulombs. Now it's 1,000 microcoulombs because it has 10 times the capacity to store charge. And then you could work your way backwards and you could say, all right, well, each of these have to be 10 volts.
Mr. Lindbergh?
Yeah.
You have to solve for that, or can you know that it's already 10 volts, so can't you just figure that out?
You could. You're absolutely right.
Okay.
And just sometimes it'll ask a question like, hey, what is the total charge? You know, that type of thing. But yeah, you're totally right. 400, and then this would be 200. And then, good? Okay. Anshul Esther, good? Okay. And then, really the only other thing would be where we have capacitors where it's, you know, like we were working on in class yesterday. You know, something like this. Do you guys want me to work through one, or do you guys feel okay? Esther? Okay, so you guys are good? Okay. Is there anything else I can do for you today?
Could you quickly explain discharging kind of when the battery's not connected?
Sure. So here, really I want you to think, so okay, so let's say I have there's some switches here. Okay. So at the start, Anshul, let's say that this switch is closed and this switch is open. Okay. What's going to happen is it starts uncharged and then it's slowly going to get charged until, because the only thing in my circuit is the battery and capacitor, until this would be equal to the voltage of the battery. So far, so good?
Yeah.
And so it would take some time to get there, but eventually it would get up to here, okay? Well, then if I open this and I close this, Now what's going to happen where this would have built up a positive charge. Oh, this would have a negative charge. Now what's going to happen is charge is going to flow around that way. Do you understand why?
Could you explain why it does that?
Because, do you understand why this plate is going to get a positive charge?
Yeah, I did.
And then conventional current goes from positive to negative.
Okay, got it, yeah.
Okay. So then what's happening is, hey, when I was hooked up to the battery, it charged up. Now, all these positives don't like hanging out with each other. So if I hook up a circuit where they can leave, they're going to discharge, and it's going to slowly move back down. So that, hey, like this positive charge is going to move around, and it's going to cancel out one of these. And then as this happens, my capacitor gets more and more neutral until it ends up with no charge at all, and my capacitor is just neutral.
So then, like, as the positive charge is moving, it creates, like, that temporary current, basically?
Right.
Okay. All right, that makes sense.
Anybody else? Thank you for the questions. Okay. Do you guys need to hear a dad joke? You want to hear one dad joke before you go?
Sure.
Have I told you guys how I used to want to be a banker? Did I tell you this one?
No.
Yeah. See, when I was younger, I really thought I maybe wanted to be a banker. I just lost interest. No.
That's good.
No.
That's a good one. That's a good one. Yeah.
That's
All
a good one.
right. Did I tell you last night I dreamt I was a muffler? It was terrible. I woke up exhausted.
That one's better. I like that one more.
That one's better?
Yeah.